Dr. Cohen?
Yes.
Did you get the live stream working?
Yes, we are streaming right now.
Okay, all right, cool. Did you get the live stream working?
Yes, we are streaming right now.
Okay, all right, cool.
Good morning, everyone. Good morning, everyone, and welcome to the second lecture for CS 2100. Before we begin on today's lecture, I'm just wondering, do you have any questions about the first lecture or any other issues?
I have a question. What day of the week is the homework normally released?
Your homework is normally released, basically, the way it's released is it's always after the previous homework is due, which is usually the day before we start on a new chapter. So next week, your homework is due Wednesday night at 11:59. And we start the new chapter Thursday, and the homework will be released Thursday at 12:05.
Okay, thank you.
Any other questions? Someone asks the question that they think 6 to 13 look unfamiliar. Are they corresponding to next week's uploaded lectures? They are corresponding to today's lectures and Tuesday of next week's lectures. Okay, so we're going to cover a lot. If you look on the first page, it says which sections the questions correspond to. And today we're doing section 1.3. If you look at the to-do list, it said to read section 1.3 at least and look at the pre-recorded lecture for today and do the pre-lecture problem set for today. Those are the questions in 1.3. And then on Tuesday, we will do sections 1.4 and 1.5. As of yesterday afternoon, I believe, but tell me if I'm wrong, the pre-lectures have been available since, since the beginning of the week. The pre-lectures and the pre-lecture videos have been already available on those sections. Okay, so if anybody wants to work on them over the weekend, that's totally possible. Okay. All right. Are there any other questions?
I noticed that the LaTeX template doesn't have any of the questions posted. Is it okay if we add the questions to those, or would you prefer just having the solutions by themselves?
It's okay if it helps you do your work to add the questions. In some sense, that's a good idea. For us, it's easier to make the template that way, but it's easier for you, I think, maybe to write the questions, especially on homework where it doesn't matter. I mean, you're not on a time constraint. So it may be well easier for you to write the question to make sure you're answering the right thing and double check it. These questions are not book questions. So you may want to do that, but it's not required at all.
Okay, thank you.
You're welcome. Any other questions?
Yeah, I have a quick question.
Yes.
If we write the assignments with colorful pen, Are we gonna get docked points?
Colorful pen. What does that mean?
So like different colors as opposed to, I know black is like the industry standard, but I'm just asking hypothetically.
Well, blue is a good color, dark blue, but if you're looking at things like red and green, it has to show up clearly in Gradescope. And sometimes when you upload them, other colors don't show up well.
I'm using
So-
OneNote.
I'm sorry?
I'm using OneNote, ma'am.
You're using OneNote.
Yes.
Well, then OneNote now automatically does black unless you change the color. OneNote, wait a minute. I don't use that, so I don't know.
Okay. All right.
Um,
It wasn't that serious of a question. Sorry.
Okay. Okay, so another person asks that the online textbook made her do a lot of questions. Is the actual book like that? First of all, that's not the online textbook, the web page that I gave her. There is an online version, but that's exactly the same as the text. So if you go to the publisher's website, what you see there are problem sets that help you learn the material. That is not the textbook. So you need the textbook for this class. I think you'll have a hard time if you don't, but I have seen that people can get online versions of it and pay or rent for the period of time that they're in the class. I have not seen that, so I don't promote it. But if it's the same book and the bookstore has that available, that's fine. But a typical thing that says go to the publisher's website and it's free, that's not the online textbook. Except for the Wednesday help, do we have any TA help sections? Yes, there are TA help sections every day of the week. If they're not available showing, have you looked on the calendar?
Yeah.
Okay, well, the calendar should show it. If it doesn't right now, we'll be sure to start putting it in. The reason we don't just list everybody's office hours for help is that sometimes some TAs have a regular office hour, but something may come up in their schedule and they won't be able to make it. So in that case, another TA may switch with them. And so we wanted to make it clear to you by listing the Zoom IDs and passwords in the, I think wherever it is, the weekly whatever page, by listing it there, then you can look and see what TA is on and then go to that, the Zoom ID for that. If it's not there, it should be there shortly. I'm sorry. But there are office hours for TAs Monday, Tuesday, Wednesday, Thursday, and Friday, every day. Okay? And I have office hours on Wednesdays from 1 to 3, and I will answer questions. So it's okay to come to me for homework or other problems. Okay? I'm not just there for the biggies. I'm there to help you as well. Okay, what else? The calendar doesn't show the Thursday lecture. Well, I think we'll have to look at that because when I last checked it, it did. So that's really weird, but I will check that after class today. Any other questions? Okay, well then let's get started on today's material. All right, so today we're going to talk about some new material and it's called propositional logic. Now it's not new if you've read the book and watched the pre-recorded lecture. So I'm going to review the concepts and please feel free to ask questions if you have any about the material. And then we're going to do lots of problems, okay? And I hope that it helps you. Remember, please stay muted unless you have a question. You can raise your hand to ask a question in Zoom, or you can ask in the chat the way a bunch of people already asked. And that will be monitored. And if I ask a rhetorical question about how would we proceed, it's okay if you want to unmute and respond to that. Unless, I mean, I don't care if I hear 100 voices say the answer, that's great. Might get a little loud, so don't yell it, okay? So let's review this problem. And this is a problem about number sequences. So the problem says, given the closed formula, do you remember a closed formula tells me what that element, the nth element in the sequence is by just knowing its place, n. So here's an example. That's a closed formula. And it says, what are the first 5 terms of the sequence? And then tell me a recursive formula for that. And remember, a recursive formula is a formula where each term is described in relation to a previous term or terms. And I think I have an example, one of the examples that depends on more than one previous term as well. I may have saved that to the end or for Tuesday as a review. A closed form, as we see, tells us we can name any place. I can tell you what A25 is right now. I don't have to work through A1 through A24 to get there. So let's work on it here. Okay, so let's do the first 5. Let's do A part first. The first 5 terms. So A1 is equal to 2 to the 2 times 1 minus 1 minus 1. And that's equal to 2 to the 2 times 1 is 2, minus 1 is 1, minus 1, which is just 2 minus 1 or 1. A2 is equal to 2 to the 2 times, 2 times 2 minus 1 minus 1. And that's equal to 2 to the 4 minus 1 is 2 to the 3 minus 1. And 2 to the 3 is 8. So that's 7. A3 is equal 2 to the 2 times 3 minus 1 minus 1, which is 2 to the 2 times 3 is 6 minus 1 is 5. So that's 2 to the 5th minus 1. So what's 2 to the 5th? 2 times 2, 4 times 8, 16, 2 to, it's 32, minus 1 is 31. A sub 4 is equal to 2 to the 2 times 4 minus 1, which is 2 to the 7 minus 1. So that's 32 times 4 is 128. Minus 1, that's 127. And A sub 5 is equal to 2 to the 2 times 5 minus 1, which is 2 to the 9th minus 1. So that's 128 times 4, which is 512 minus 1 is 511. So we've done the first 5 elements. Okay, so let's see what we can come up with as a formula for this. Let's go back here and look. And A sub 1 is given. So the recursive formula would say A sub 1 equals 1. We always have to give the base case, the initial value. And then what do we have? We have A sub 2 is 7, which is A sub 1 times 4 plus 3. Notice it's not just A sub 1. We have a multiple of A sub 1 there. Okay. Now you could look at that and say, how do I get to 7 from 1? So that's one way. Now we look at this and say, well, let's see, here's A sub 2. And if I add 1 to A sub 2, okay, if I add 1 to A sub 2, I have 2 to the 3rd. Okay, but I have 2 to the 5th. So I have 4 times a sub 2 plus 3. And if I look carefully, I'm going to see that's 4 times a sub 3 plus 3. Okay, and then I have 4 times a sub 4. What? Do I have the wrong one here? Oh, what did I do wrong? I don't think so.
That looks good.
Okay, good. 3. So we have an idea that's coming along here. So our hypothesis is it's a to the sub n is equal to 4 times a sub n minus 1 plus 3. Okay. Notice that when we were working it out and giving the first 5 terms, even though we had the closed formula, what did we notice? We noticed that if we added 1 to the previous element and multiplied by 4 and then subtracted 1, so what did we do? We said the next one is equal. I take the last one that was a sub n minus 1. I added 1. I multiplied by 4. And then what did I do? I subtracted 1. And that's was sort of the idea that we did when we worked out each of the first, the second, third, fourth, and fifth term. That's how we worked it out, basically, instead of just computing, gee, I have to do 2 to the 5th, so I'll do that all the way from scratch. No. We looked at 2 to the 3rd and then just multiplied by 4 and then subtracted 1. So basically, that gives the idea of how to get the recursive form from the closed form. Okay? Okay, good. So let's look at the logical operators as a review. Now, the logical operators, they're really nice because we can translate things. Now, first of all, we'll talk about a proposition is just a statement. It can be true or false. It has to be either true or false. It can't be, well, I'm not sure, sometimes this and sometimes that. So a statement, proposition is a statement that is either true or false. It's not a question. It's not a command. So variable letters are used to represent propositions. On Tuesday's class, we're going to talk about more complex constructions called predicates. And that's where we are allowed to have things that, well, I have variables, and if I put in a value, then it becomes a proposition. But that's not today. Okay, so today the statement has to be either true or false. The operators that we can use to join these together are and, which is denoted by the upward caret here, or, which looks like a big V, and the negation. Now, and or are binary operators. We have, it's in fixed notation. We have a proposition on one side, an operator, and a proposition on the other side. The not operation is a unary operator. And that means we have the not symbol and then a proposition, I guess with yours like that, a proposition after it. Okay. And that changes it. If it was true before, the not says, well, it's the opposite now. Question. Dan.
Yeah. So I had a question about getting the recursive formula from the closed form formula.
Yeah.
So instead of looking at the sequence and constructing the recursive formula based off the first 5 terms, could we just take an and subtract an minus 1 and then add an minus 1 to both sides to obtain the recursive formula?
Sorry, tell me again, and I will try writing what you're saying if I understand it, and then I'll let you know. Tell me what I should do, and then we'll see.
So since we're given the closed formula, we can write out
So you
the
want to
term
write
a n
sub
minus 1,
n. And then what do you want to do with that?
subtract a sub n minus 1. And then
Okay.
based on that difference, that
So we
should give
have
us a
2
formula
to the
where we can
2n
add.
minus 1, that's a sub n, minus 2 to the 2n minus 1, whoops, that's a 2, n minus 1, minus 1, minus 1. Is that what you want to do?
Yeah,
Okay, let's look at what we get out of that. That's equal to 2 to the 2n minus 1 minus 2 to the 2n minus 3, if I compute right, plus 1. So that's equal to 2 to the 2n minus 1 minus 2 to the 2n minus 3, which is equal to 2 to the 2n minus 3 times 2 to the 2 minus 2 minus 2? No, plus 2 minus 1, which is 2 to the 2n minus 3 times 3. Now what do you want to do? I got
I
a 3
wanna-
there, so that's got to be the right idea. What did I do wrong? Did I do what you did?
yeah, that's what I did. And then I added a n minus 1 to both sides so that I could put the nth
So
term in
then
the
we're going
sequence
to
in
get
term of
that
the
a
previous.
n minus n is equal to 3 times 2 to the 2n minus 3 plus a n minus 1. Is that what you're saying?
Yes.
Okay, let's see what that is. Well, that's okay, but here I have this sitting in there. There's a 2 to the 2n minus 1. So I have another n there, but I don't need it. I can do it with a constant instead. It's always better if you can get rid of the 2 to the 2n minus 1. What you have is not the simplest form. It's not bad, but it's not the simplest form. So it's not what I'd like to see.
Okay. Sounds
Okay.
good. Thank you.
Sometimes, wait a second, sometimes taking the difference is exactly the right way to do it. But for this problem, it's not exactly the right way. Okay? All right.
Thank you.
Any other questions? Okay. So a logical constant is a proposition that always has a single value. Now that seems kind of silly, but we're going to look and see what that means in some of our examples. A tautology is a logical constant that represents a proposition that's always true. A contradiction is a logical constant that represents a proposition that's always false. Okay, so let's see what we have here. So if we're looking at something, there's something called the truth table. And a truth table is the way for a logical expression to determine under what conditions it's true and what conditions it's false. So the way we do logical expressions is the first thing we do is we make logical expressions that are combinations of propositions and operators. Okay, and remember that and or are binary operators and not is a unary operator. So there's a precedence, just like in arithmetic, there's a precedence. Here we have that not is the highest order, then comes and the lowest order is or. So if you see them showing up without parentheses, you just follow the symbols of precedence like you do when you do arithmetic. Parentheses overrule that, and you always do what's inside first. Okay? So a truth table is a mechanism for enumerating all the possible relationships. So if we look and we say, well, tell me what the and operator gives as a result. And we look at that and we see, well, notice something here. Okay? Notice I have a truth table here and I list all the possible combinations. Now, if I have two variables, which is all I have in the case of a simple and, we see that how many combinations? Well, P can be true and Q can be true. P can be true and Q can be false. P can be false and Q can be true. And P can be false and Q can be false. So we have 4 possibilities of combinations. So we have to enumerate them all in a truth table. Okay, so that's the first thing we have to do. And in order to make a truth table clear and easy to understand, what we're going to do is start from the right of all the variables, however you enumerate them. We have Q is second here because it's second in the expression, but we vary that one fastest. Okay, it's just like when you have a time, the second hand goes fastest, then the minute hand, and then the hour hand. We go from the smaller to the larger, from right to left. And it's also true on a truth table that it's easier to read the truth table and easier to be consistent and understand it when you enumerate the possibilities like that. So here we have the second one changing first. So for every value of P, we have 2 values of Q. And then we have the next set of values for P and 2 values for Q, because we only have 2 values, true or false. Okay, so what we see is that P and Q says they both have to be true. So if both are true, P is true, Q is true, then P and Q is true. I woke up this morning and I ate breakfast. Now, some of you all woke up or you wouldn't be here, but some of you may have woken up and not eaten breakfast yet. So that may not be true, that part. So here we have, that's the case where we have true for the first one and false for the second one. And that leads to false because you didn't do both of those things. I said and. Or you could say, well, I didn't wake up, but I ate breakfast in my sleep. Well, then you didn't wake up. So it's false. You didn't wake up and eat breakfast. And then here's the case where you didn't wake up and you didn't eat breakfast. You're still upstairs sleeping. Okay, so that's the case where you did neither. So the answers in our truth table are true, false, false, false. So in an and operator, it's only true when both of the arguments are true. Then we come to the or operator. And this is true if either one or both are true. So in that case, we have the first case, you would say, I woke up this morning or I ate breakfast. Well, that's not a good example, but we'll go with it anyway. So in this case, you woke up and you had breakfast too. So in that case, the or has both of them are true and the answer is true. The second one is I woke up, but I didn't eat breakfast, but that's still true because you woke up. The third one's I didn't wake up, you ate breakfast. So it's true because you did one of them. And the fourth one is false because you didn't do either one. I know in computer science, we're used to having something called an exclusive or. The or operator here is not the exclusive or. They both can be true. When I ask you, do you want ice cream or cake for dessert? I'm not saying you can have both. That's exclusive or. Although my grandkids would like both, but you can't do that. Okay? Now, the not operator, notice we have just one argument. So our truth table is only 2 elements long, and it flips the bit. So if P is true, not P is false. If P is false, not P is true. So here's the big question. How many rows are in a truth table? Well, there's one, that's the header. And then how many combinations can we have? Well, each column, each proposition can have two values. It can be true or it can be false. We don't have our coins stand on end, either true or false, nothing in between. Okay. So in that case, the number of possible combinations is to the number of arguments. Okay. So here we had 2 arguments. So we have 4 rows. If we had 3 arguments, we'd have 8 rows. Okay. And the rightmost row is the one that varies fastest. Okay. It's also a way, sometimes students don't do that. And then they find out they've left out rows and they get questions wrong on exams. So that's also another way. You can't make that mistake if you just carefully move them along so that the rightmost bit is the one that changes fastest. Okay. You can think of them as bits if you like. Okay. But we don't use ones and zeros in this class. This class is wedded to trues and falses. Okay. All right. So here's an example. We have a truth table that involves, what does this one say? This one says not P or not Q. So how many columns do we need? Well, in order to get full credit on homework and on exam, you need to show all the intermediate steps. So here we have P and we have Q, and we have not P, which appears. And then the intermediate step is P or not Q. That's this column. And then the last column is the one we're going for, not the quantity P or not Q. Okay, so let's fill this in. I already filled out the table. Notice my right variable varies fastest. The first one varies slowest. So here we go. Okay, we have not Q. Well, not Q just flips the bit. So where we have true in Q, not Q is false. Where we have false, not Q is true. Where we have true, not Q is false. And when we have false, not Q is true. Now you could say to me, that's so straightforward. Why do I have to have a column for that? Well, because when you're doing these complex truth tables, you can forget and you can really mess up. But if you have a column for it, you're much less likely to mess up. Okay, so don't forget that. So here we're asking P or not Q. So what do we have here? We have P. We're comparing the first column and the third column. So we have P is true and not Q is false, but one of them is true. So that's a true. And then we have P or not Q. You have true or true. Well, that's definitely true. And then we have false and false. That can't be true. That's false. And then we have false and true. So that's true. Okay. And now we go not that quantity. So then I have false, false, true, false. And we've done it. Are there any questions about this?
Question about something else.
Who's that? Alec, yes.
Hi. How picky are you on notation for homework and exams? Like, for example,
Picky.
Okay, so we have to use this not symbol, not like a little tilde or anything?
That's right.
Okay.
If you're using a computer, it appears in Word. The not symbol is under the symbols. And if you're using LaTeX, it's \not.
Okay, thanks.
And if you're doing it by hand, then you're doing it by hand. Okay. All right. So here we have a truth table and we have only one proposition. We have P or not P. So here's my column for P and here's my column for not P. So if I have true or false, well, that's true because one of them is true. And I have false or true, that's true. Okay, so that says that this logical expression is a tautology. It's always true. Okay, always true. Yes, Ethan.
So I just have a bit of a question about homework and exams. So like if I wanted to, on the not P or not Q thing, if I
Yes.
wanted to apply De Morgan's laws to reduce the number of truth table rows I'd have to fill out, is that okay? Or should I leave the expression in its form?
When you're doing truth tables, generally you use the expression in its form. We don't get to De Morgan's laws until a little later here. And when we get to De Morgan's laws, that's when we're using the substitution principle. So typically you will use either a truth table or the substitution principle. Usually you don't combine them, okay?
Okay, thank you.
Okay. Continuing. Here we have a more complex truth table. Okay, what do we have here? We have P and not Q, or not P and Q. So here we have way more columns. We have the same number of rows, but way more columns. So we have a column for not P, a column for not Q. We have a column for P and not Q, and a column for not P and Q, and then one for the whole expression. So I've already filled in P, Q, not P, and not Q. So all we have are 3 columns left to compute here. Okay. So let's see. So P and not Q, we're looking at these 2 columns. So true and false is false. True and true is true. False and false is false. And false and true is false. So this first one only has one true location. Then we do the the 4th column, which is not P and Q, those 2. And we get true and false is false. False and false is false. True and true is true. And false and true is false. Okay, so now the answer is an easy answer. So we just look and we say, well, false or false is false. True or false is true. False or true is true. And false or false is false. What operator is that from your computing experience? Do you remember? You have any ideas? Christopher.
Sorry, that would be the exclusive or. I had
That is the exclusive or. And the exclusive or is frequently written XOR. Okay. It also has other symbols. Some books and people write it like a plus sign with a circle around it. That has another meaning in other areas of mathematics, but that's good enough to go now. So the exclusive or means either the first is true or the second is true, but not both. Cake or ice cream for dessert, not both. Okay? That's a good one. All right. Construct a logical statement that is true when P is true and Q is false. Does anybody want to take a stab at this? Or does everybody want to work on it for a minute? David,
Wouldn't it just be P and not Q?
P is true and Q is not. Very good. Very good. P is true and Q is false, or when P is true and Q is true. Oops, sorry about this. Sorry about that. Okay. P is true and Q is true, or P is true and Q is false. Or when P is true, Q is false.
Wouldn't that always be true?
I think it would
So
just
what
be,
do we have?
Or sorry, not always. It would always be P.
Sorry, P is true and Q is false. We got that one. Or what is it?
I think Q is saying it's just plain P because it's always based on P.
Well, let's just do this one first. Or P and Q. We're going to have another rule shortly that will get us to P on that, actually. Okay, that shortens that. So let's just wait a second. And
think your middle symbol is
The middle symbol.
or, whoop,
We-
sorry. Thank you.
Or.
I appreciate that. I said or, my brain and my fingers did not do the right thing. Same thing. Okay, either P is true or Q is true and R is false. Remember our logical symbols of which one has precedence? So we have Q is true and R is false, or P is true. Now in English, it's not so clear. But in the logical expression, it is. Okay. Okay. Okay, so here we have a truth table. You come across two people on an island that this is usually called Smullyan's Island. These things are sometimes hard to figure out. It says A says we're both telling the truth, and B says A is lying. Who, if anyone, is telling the truth? So I'd like to go through this with you. So we have P is A is telling the truth, and Q is B is telling the truth. Can you read my writing? I'm trying really hard, but I don't write very clearly. So tell me if you can't understand it, please. Okay. So what do we do in the truth table? How many variables, how many inputs do we have? And how many outputs do we have? We have two inputs. Oops, I think I have this on the next page. Nope, got to do it right here. We have P and Q Now, if P is telling the truth, we have P says we're both telling the truth. So that says P and Q, both telling the truth. So this says A says P and Q. And then we have B says, what does B say? B says A is lying. So we have not P. Okay. So let's fill this thing in. We have true, true, false, false, true, false, true, false. Okay. So we fill this in. So we have true, false, false, false. Just looking at this truth table, we fill it out. So here we have not A, or not P, excuse me. So that would be false, false, true, true. So tell me, does anybody know, or can anybody tell from the truth table who is telling the truth and why do you know that? I'm happy to go through it. I just want to know if anybody got it already.
Is it B? Because for B is the only statement where in the situation of the third situation of P being false and Q being true, P and Q is false and not P is true.
Yes, you're right. Let's go through the logic row by row, okay? So in the first row, if A is telling the truth, then they're both truth tellers. But if B is telling the truth, then A is lying. So how can A be telling the truth and lying at the same time? Okay. So this says A is lying, and that says that he's telling the truth. Can't have it. Okay. In the second row, it says that P is telling the truth. Well, but I'm sorry, P is the truth and Q is lying. That says A is telling the truth and B is lying. Okay, but if B is lying, B is saying that A is lying. So that would mean A is telling the truth. And here it says that not P is false. So that one doesn't work either. And then down here, it says that A is not telling the truth and B is not telling the truth. And this says neither A nor B is telling the truth, and A or B is false, not B is false. So A can't be lying because this column says he's telling the truth. So here we have that he's lying, and here we have that he's telling the truth. Can't have that either. So this is the row that P is false, both are not telling the truth. Q is true when he says A is lying. And here P and Q is not true because A is lying and B is telling the truth. And here, not P is true. Okay. Both are not telling the truth. So very good job. That's a hard one. Okay, next one. You come across 3 people on an island. Let P represent the statement A is truthful. That's P. Q represent the statement. B is truthful, and R represent the statement. C is truthful. Now we have 3 variables. Write the following sentence in symbolic logic and notation. So what do we have? A is lying, so not P. That's the highest precedence. And is next. Q or R. Okay. Yes, Dane.
So are these precedence rules axiomatic? So do we assume them at the start when we study logic, or do they pop out of
No, they're the
more
rules.
fundamental?
They're the rules. There could be some logic elsewhere that had totally different precedence rules, but not propositional
Okay.
logic. Okay. Joseph.
Thanks.
Excuse me. I'm still kind of having a hard time understanding how you came to the conclusion in our last example that
That one.
he was telling the truth. I couldn't follow your logic very well with that one. So could you kind of go over that one more time?
Sure. If A is false, he's saying both are not telling the truth. Okay. But here, so whatever value P is, not P is the opposite value. So that says that he's telling the truth when he says that both are telling the truth. But that can't be. So I'm sorry, that's the wrong way to phrase that. So if A is false, that means that the quantity A and B is false. If B is telling the truth, it means that A cannot be telling the truth, i.e. that A is not true, that they are both not telling the truth. That means at least one of them is telling the truth.
Okay. I
Okay.
kind of I understand that, but like, are you using the truth table to come to that solution, or you kind
Oh
of?
yeah, it's really hard to tell otherwise. You're looking here, and that helps you understand. How would you be able to figure out all the different cases without the truth table?
Okay, gotcha.
Who else do we have? Steven, remember to put your hand down. Yes, Steven.
I was just saying, Joseph, if you're still confused, I could try to explain it in a different way, or do you think you're good?
I'm sorry, what?
Oh, sorry, I was asking if Joseph was still confused, I could try to explain it in a different way,
Oh, okay.
or
I mean,
Well,
yeah,
if you
sure. I
want
would
to do
love
that in a helper study
additional
group with each other, that
explanation.
would be great. But I think we should move on. In
Okay.
fact, whoops, we are running late and we have to have a break. Phew, have a break. I'm going to have to move along so I can cover the other material. So while you're on break, I'm going to figure out what I can skip of these problems, but it will be in the notes. Okay. So we're going to take 5 right now. Okay.
I put a big wall of text in chat in case anyone wants to see at least how I think about it.
Thank you, Stefan. That was very helpful. Well worded.
Oh, no problem. Yeah, I even before was like getting lost in my own head, like, wait, true, false, how does it, and then I was like, okay, step back. So, yeah, no problem.
Yeah, I think I was just getting too caught up in like the individual columns and rows of the truth table.
Yeah, but me still, I was on it, and I'm like, wait a second, then if this is true, then that makes that false. And I was like, so, I mean, it does help, like, at least for me, like, break up the different, like, possible options. But yeah, it can sometimes get kind of confusing.
Hello.
Cat time.
Now your cat will forever be immortalized on YouTube. Say hello, Ellen.
That cat
Oh,
is a
okay.
tautology.
Get off the spaceport.
Okay, let's resume. I'm skipping a couple of expressions that we worked at. I see there was a big conversation on the truth teller problem. I'm glad if that helps people understand it. Great, thank you. So it turns out that there are a lot of properties of Boolean operators. And you can prove these properties with truth tables. That means that if you made a truth table and put in all the possible values and put the expressions, you would see in each of these cases, wherever my mouse is, you would see in each of these cases that you could put a column for the left side and a column for the right side, and the truth table would indicate that they would have exactly the same values in the same rows. Okay, so there is a first statement that says that if you have two statements that are equivalent, it means that their truth tables are identical. If their truth tables are identical, you can substitute one for the other wherever you see one of them. Okay, so here are some of the rules that follow from that can be shown in a straightforward way with truth tables. There's the commutative property, and you know the commutative property, and many of you take it for granted. That's like saying A and A times B is the same as B times A, and A plus B is the same as B plus A. Sometimes we think of and as a multiplication operator and or as an addition operator. Some of these rules that hold for logical operators do not hold for arithmetic. So don't get too wedded to the notion that they have the same rules. Some of them are, but not all of them. The associative rule, notice we have 2 operators and 3 variables with the associative rule. And that says if I do the first and get a result and then apply the second and I will get the same thing as if I do the first, I'm sorry, as if I do the second and third operators, the second and then get a result and apply the first and. Similarly with the OR operator. Notice the associative operator has 3 variables, it has parentheses, but it has only 1 operator. Okay, 1 operator. Sometimes people write it without any parentheses when you're doing associative because they're equivalent. But you can't do 2 operations at once. You always have to pick one to do. So if you see a problem like that and you're told to apply to show that 2 things are equivalent, the first thing you have to do is take it and apply parentheses where you want them. The distributive operator sometimes gets confused with the associative operator because there are 3 variables, but they're different operators, one inside the parentheses and one outside the parentheses. Okay? And the same rule applies when you flip the operators. You get different results. So what does that say? That said, the first one, the left column says P and the quantity Q or R is the same as P and Q or P and R. Okay. The right one says P or the quantity Q times R, Q and R, sorry, is the same as P or Q and P or R. Notice that the ors are in parentheses and they take precedence because they're in the parentheses in the right case here. Here's one where you can't get hung up and think it's like arithmetic, because this left one is kind of like arithmetic if that's a multiplication and that's an addition. But the right one is not true for normal arithmetic, but is true for logic. Okay, so don't in your mind say, oh, it's just like arithmetic. It isn't, it's different. Keep them separate in your minds. The identity rule says PE and a tautology. A tautology is always true. So it takes the value of whatever P is. P or a contradiction. Contradiction, remember, is always negative. So then it takes whatever P's value is, because only P can be true. The contradiction is never true. Negation says that P or not P is a tautology. Any statement is either true or false. It can't be both true and false. It's either true or false. Okay. And here's another identity, that P or contradiction, I'm sorry. We're down on this statement. That's negation. Sorry. P and not P can't happen. Something cannot be true and false. Okay. So that makes it a contradiction. Always false. The double negative. The negative of the negative is the original statement. So if the original statement was true, the negative of true is false, and the negative of false is true. Okay, that's the double negative property. That one turns out to be real. All of these turn out to be really handy. Idempotent, P and P. If P is true, then P. P or P is also P. I mean, there's nothing else you can cut out of that. That's called idempotent. If you apply an operator twice, it's the same as the original there. I mean, if you apply an operator, it's the same as the original. De Morgan's law. Now, De Morgan's law has an operator in parentheses and the negation sign. And it says that that's exactly equal to the negative of the first proposition. You flip it from an and to an or, and then it's the negative of the second proposition. Notice when you do this, you can go from right to left. Okay, so when you have a negation symbol and a single other operator, it's possible to apply De Morgan's law. And then De Morgan's law comes across on this side too, where you have the negative of the quantity P or Q. What does that mean, the negative of the quantity of P or Q? If you say P or he goes to the beach or he goes to the movies, to say the negative means what? It means he doesn't go to the beach and he doesn't go to the movies. Okay? De Morgan's law is sometimes confused with the distributive law and the associative law. It's different than both of them because associative and distributive don't have any knots in it, and they have two operators. So be careful. Then we have the universal bound. P and contradiction is contradiction. It can't be true whenever contradiction is with an and. P or tautology is always tautology. If it's an or statement, the tautology is always true. So the result is always true. You say, why do I have to do this? Because when you're simplifying expressions, things come up like tautologies and contradictions, and you need to know how to use them. Remember, they come up in the identity, and they come up in the universal bound. Absorption. Absorption says if you have P and the quantity P or Q, that's equivalent to P. You can show that using the distributive law. And what else? And the idempotent law rule. P or the quantity P and Q is P. Again, you can show that using the distributive rule and idempotent. The negation of a tautology is a contradiction. If something is not always true, then it's always false. If something is not a contradiction, then it's a tautology. So those are the rules. So the first thing we have to do is apply them. So we already said that you can replace any expression on the left with an expression on the right, or that's on the right with the one on the left, when they're equivalent without changing the truth value. These are De Morgan's laws again, okay? And here's a nice, easy problem to say. If Sue is both a junior and an English major, if she's not both a junior and an English major, then she can be not a junior or not an English major, okay? So when you're applying De Morgan's law, when you go to not on either statement, you're flipping the operator in between. Okay, let's do one. So, sorry. Okay, we're going to apply this theorem. So we have P and Q and R. Do we have the same operator there 2 times? Yeah, we're going to apply associative there. Or P and Q and not R. We want to show that's equal to P, equivalent to P and Q. So the first thing we do is we see that there's a P and Q as part of both of these. Okay, so let's apply the associative rule, and that's P and Q and R, or P and Q and not R. Okay, now that's the associative. So what's the first thing that you think we can do? What do you see here? I see something. Let's look on the right side of an expression. So we look at that and we say, that's the P down here. That's the Q in that operator. This is the P down here. And that's the R in that operator. I know we're using P, Q, and R, and it's a little confusing, but let's apply the distributive law from right to left here. And we get, this is the P in that operator. And what do we do here? We say, oh, wait a minute, I had the OR was in between here. And the AND, see the AND here goes to the outside, so that's the AND. What do we have? We have R, or, not R. And what was that? That's the distributive law rule. Okay? The next one, what do we do now? Well, we look and we see we have R, or, not R. What rule is R, or, not R? We look here and we see that's the next one we're going to apply, and that's negation. So what do we have? We have P or Q, and what's R or not R? That's a tautology, so that's T, and that's by negation. And then the next one, we're going to write on that line so we can squeeze it in. So what do we know when we AND something with a tautology? That's here, 4. A statement and a tautology is the statement. So that gives us P and Q. Okay, now, what do we say with that? What was that? That's identity. Now, if you have a problem such as this on the homework, you have to put every single step in. You can't leave it out. One of the steps students frequently leave out is commutative. Okay, if you see something here, for example, we have something here that's P and the quantity Q or R. If you see something that says Q or R and P, you have to apply the commutative rule to put it in the same form that it's here. Oh, we have 3 people here. Who raised their hand first? I'm going to do it in some order. Britton, you first.
Yeah, I was just wondering, so you said that we need to list each of the steps, and that makes sense. Do we also need to list the rules that we use, like write those out?
Well, you don't. You just have to say what it is, like associative or distributive or identity or negation.
Yeah, so we need to write those like words next to the steps.
Yes, you do.
Okay.
Some people write it before they apply the step. I don't. Some people write it above the equivalent sign here saying what they're doing as they're doing it. That's perfectly fine. Or in the line that you've applied it, that's perfectly fine. Okay? Lewis.
So I had a question about how to like process all of these different identities. Do you recommend us for future problems? Because I imagine these identities are going to come up pretty often in this class.
They will.
Do you recommend us studying each individual one, or just having it out on like a little like table as reference? Like, do you expect us to memorize all these for the exam?
I do not expect you to memorize them for the exam. On your homework, you can clearly use your book. For your exams, you will be allowed to make a cheat sheet.
Oh, okay.
And I may provide them anyway. I haven't decided. They're really important. What happens if you don't do enough practice, if you say, oh, they're listed, you will spend a lot of time looking it up. But if you do a lot of practice, you'll recognize that, gee, that's one I know how to apply, and you'll know to look for it.
Right.
Okay. So
Okay.
do lots of sample problems so you get familiar with what the rules are that you can apply. Okay.
All right. Sounds good.
Tyler.
So I'm just a little confused as to how we got to where we were after we did the distributive property. How we went from
Distributive to
P.
negation.
No, because I understand how to do the negation step. I'm wondering how we got R or not R.
Ah, that's the distributive property. That's where
Yeah.
we applied it. Because you see here, look, if I call this operator, okay, let me call that capital, not capital. Let me call that PQ, or let me call that statement S. And let me call this statement T. And let me call this statement U. Then this is of the form S and T, or S and U. And if you look under the distributive law, the left column, the right side of it, it looks exactly the same if you substitute S for P, T for Q, and R for U. Do you see that?
Oh, okay.
Oh, okay.
So I thought we were taking the R out, but we took out the P and Q.
We took out the
Okay.
P and Q because they were the same in both expressions. R, in one expression you had R, and the other you had minus R. So you can't take it out like that. Okay,
Okay.
good. Jamal.
In all common areas.
Can you do this as a two-column proof?
Helps on the spread of COVID-19.
What do you mean a two-column proof?
Well, like similar to how it's laid out in geometry, where you have one column that is like the property that you use, and the other column is just like, this is the statement, and this is how it changes, and this is how it changes.
So that's what I've done if I don't have a lot of room here. But when I say equivalence, that's the column. The first column is what you're saying, and the second is the property we're using. So it's effectively what you're saying, but not written in a column form.
Yeah.
The equivalence says it's equivalent every step of the way. Okay. Good, thank you. Put your hand down now. Lewis.
Sorry, I still had my hand up.
Okay, good. Let's do another problem. Got more of them. Got lots of them, actually. Okay, so prove using theorem 2. I'll take out the word prove in case it's scary. Show using theorem 2 that the quantity not P or Q, and here's a double thing, the quantity P and Q is equivalent to P and Q. Okay, so we write the left one. You're always going from the complex one to the simpler one, because trying to go from simple to complex is very hard. So we have not P or Q and P and Q is equivalent to. Here's our first step. What's the first thing you see here? The first thing I see is in the second big parentheses, I have P and Q. So that screams associative, maybe, because I have P and P here. So by the associative rule, the first thing I can do is I can change that to P and Q. That's the associative rule. Okay. Now, what's the next thing we can do? What's P and P? Do we know? Do we have a rule for that?
Idempotent?
No, it's the one with the funny name. We had associative was the first. Here's the one with the funny name, idempotent.
Oh.
P and P is equal to P. Okay, Good try, though. It's okay. You can keep doing that. It's worth a try. You
Sorry,
never
I
get
think I
points
said
off
that-
for trying.
I
What?
said that I just pronounced it differently than you did.
Oh, good. Idempotent. We got it then. We have not P or Q and P and Q. And that is idempotent. Okay, what's the next thing to do? Okay, what do we see here? We see not P and P. They're not the same, but the Q's here are the same. So we're going to apply commutativity and change the order around so we can apply distributive law. So we have Q or not P and Q. Oops, that's not true. That doesn't work. We'll take that back. Sorry. Okay. Don't mind me. Gotta get the right page here. Okay. So what we can do again is we can apply associativity again. So we have not P or Q and P, parentheses around the whole thing, and Q. That's associativity. Okay. So this is like A and B and C. Okay, so we've got that. Now we have something that we've done before. So we're going to apply the distributive law, but we have to flip them. So the first thing we do is commutativity, P and not P or Q and Q, and that's commutativity. And then the next one is we just apply distributive, which is P and not P. P and not P or P and Q. Those are all still in parentheses. And Q, and that's distributive. And I have to leave the rest for you guys to do because we are out of time and I'm over a couple of minutes, and I apologize for that. Okay, so I will leave the rest of this problem. I have lots of problems here. But here's the reminder of your to-do list. Your homework is due on Wednesday. Your problem set from this lecture is due tomorrow at 5 p.m. If you have any questions on this material, why don't you send them as questions in Zoom. If you have problems with the material in this lecture, try some of these problems at home. And if you have problems, I'll try and find time to squeeze them in next lecture, or else have TAs do them during discussion tomorrow. So have a look at them tonight so that the TAs can do some of them tomorrow if they need to, okay? Good. With that, thank you all.
Thank you.
Yeah, thank you.
Thank you, Professor.
Thank
you, Professor.
Thank you, Professor Cohn.
Thank you.
Thank you. Bye-bye.